So having talked about central tendency or middle scores of data, the last major piece of the descriptive statistics puzzle is thinking about variability. And to demonstrate the importance of variability, we can use a simple example of two golfers hitting balls to a golf hole. So let's say we've got player A here, he hits a series of shots, and you can see on average, or we calculate on average, he hits the ball 10 centimeters past the hole. So you can see on the left there, we're just measuring how far past or how far before. So on average, 10 centimeters past the hole, this sort of representation. We might then have another player come along who also averages 10 centimeters past the hole, but he's gotten much closer to the hole each time. So if we put those side by side, we can see that whilst that average score of 10 centimeters past the hole may represent an important part of the data, the variability, or how far away, how different each of those shots were, starts to become important. So hopefully you can see from that very simple example that variability is an important aspect of the data. In fact, many times variability is the most important aspect of the data that we collect, and especially if we start thinking about further inferential statistics that look at what causes differences between individuals or even between different performances of the same individual, you can start to understand that variability is going to be a really important measure, both in how we understand the data, but also how the actual methods that we undergo to look for differences as well. So the three common measures of variability that we'll go through in the subsequent section of this presentation: range, variance, and standard deviation. So the first measure of variance we'll talk about, and probably the most simple, the one that all of us would likely already know, is the range of the data. So if we just look at this graph and consider every dot as a individual data point taken from a participant, and we just look at the x-axis, we can simply have the difference between the bottommost score and the topmost score. So let's say that the tallest person in the room is 190 centimeters, the shortest person in the room is 160 centimeters, so therefore there's a 30 centimeter range. This is a really easy one to calculate and gives us a very quick rough idea of the spread of the score, but it doesn't tell us really how people sit within that spread. So maybe the data will be very different. Maybe they're mostly sort of clustered around the mean, and maybe they're further out towards the edge of those ranges. It's got fairly limited information from that perspective. So that leads us into the next couple. So the next of the measures that we can use for variability is variance. You likely would have heard of this before. Maybe you've wrapped your head around what it is, maybe you haven't. Essentially, moving on from the range, it starts to give us a bit more detail about individual scores within the set. So if we consider the average within this set here on the x-axis to be that line, we've just drawn a line through the average score, we can start to consider what the differences are, or how far each of those scores are away from that mean. So specifically, variance is a measure of variability that considers all the values and calculates the distance of each from the mean. So these distances from a mean of each value is called a deviation. And so the variance is simply the sum of the deviations squared divided by the number. So let's make sense of this a little bit more with an example. So if we say that we've got 5 individuals here, and I've given them all a math test, and the maximum score on that math test is 20. So one of them scored 8, one of them scored 10, one of them scored 12, one of them scored 14, and one of them scored 16. Hopefully it's pretty obvious from looking at that the mean of that data would be 12. But if we start to look at the deviations, we can say, well, what's the difference between that first score of 8 and 12? Well, that's 4. What's the deviation between 10 and 12? That's 2. What's the deviation between 12 and the mean score? It's 0. What's the deviation between 12 and 14? 2. And what's the deviation between that mean and 16? That's 4. So we've got our deviations, and these deviations obviously give us an idea of how far each of these scores are away from the mean. Now, if we're calculating variance, the next step that we do is we square those deviations, and we come up with these numbers. So 16, 4, 0, 4, 16. We plug it into our equation, which is important, but not really the focus or the number one thing you need to wrap your head around. You need to understand that that number comes out as, say, an 8 there. So it's 40, it's the sum of those deviations squared divided by the number, which is 5, and we get an 8. What is important here is to understand that that number will get larger as the scores are further away from the mean, and they get smaller as the scores are tightly clustered around the mean. It's also important to know there's a difference between calculating variance for an entire population versus calculating a variance for a smaller sample of a population. So if we're representing entire population, variance is that top equation there. But if we're looking at just a sample of a larger population, which is most common when we perform our research, we want to be a little bit more conservative with our numbers. So there tends to be a little bit larger variance that we're not aware of when we take a smaller sample, especially when it's non-random sampling. So what we do in our equation is just have that n at the bottom of the equation. We take 1. So in this case here, it'd still be the sum of those deviations squared, 40, but instead of dividing by 5, which is the number, we divide by 5, take 1, which is 4. And that just gives us a slightly higher variance here. Same concept though, if that number's bigger, the more spread out those scores are, and it's smaller, the closer they are clustered around the mean. So variance ends up considering all of the scores and giving us a number on to represent how spread the data is. The major criticism of using variance though is the number we actually get tends to be quite high and is hard to relate back to the meaning of the original scores or even the deviations. So in this case, if we look at those deviations, one logical thing that we might want to use to represent the spread of the data is the average or middle score of those deviations. And so, you know, one of those scores is right on the mean, but then some of them, there's 2 that are 2 and 2 that are 4. So we'd likely think there's something around the 3 mark is a more representative of those average of the deviations, but that's nothing like what variance gives us. However, if we use that variance calculation and simply add a square root sign to it, so we square root the value of that 10, what we get is a number that's much closer to what we'd consider the average deviation. It's not actually the average deviation because we're not square rooting both the deviations and the number, but it's something that represents it much better than using variance. And so when we do this, when we square root that calculation, it turns out it's actually the formula for something that is the most common measure for variability, which is standard deviation. So standard deviation, like variance, takes into account all of the scores and how far they are from the mean, but it's also the most complete and common measure of variability because it gives us some indication that makes sense about how spread the data is. So for example, if I say everyone in a particular classroom has an average height of 1.75 meters, that gives me that measure of central tendency. I want to know how spread the data is. I might say plus or minus a standard deviation of 0.08 meters or 8 centimeters, and that gives you an idea that, you know, on average away from that 0.75, people are around 8 centimeters away from there. So that is the measure of standard deviation. Sometimes you might just see it reported as plus or minus, sometimes you might see the abbreviation SD in there, but that's the most common one. And the calculation for the whole population is that they're just using the number underneath, and for a sample of the population is variance for the samples, n take 1 and the square root of that. So now we have our 3 most common measures of variability. There are more out there, but one that's worthwhile pointing out to be aware of when you're reading research is the use of standard error of means, or SEM. So sometimes you'll see this reported, and what it really is trying to do, that's the calculation for it there, by the way, it's the standard deviation, so what we got in our previous calculation, and we divide that by the square root of the number. Now this is used, this has a really legitimate use in using it as an estimate of error when we use a sample as a predictor for a population. So it gives us that indication of error when we're sort of going through that process. But some use it in place of a standard deviation, and this is because it makes the number of your standard deviation essentially smaller. It reduces that number, and that can be nice sometimes when we're graphing our results and we want it to look like there's not a big not a large variability in our data, but unfortunately doing this to replace standard deviation can actually underrepresent variability and lead to misleading results. So it's one to be aware of, to watch out a little bit for. It does have legitimate use, but beware if it's not used in the correct way.